So, what do you get when a Nobel Prize-winning physicist, I'm talking about a guy who helped write the textbook on Einstein's theory of relativity, decides he wants to go make a movie? Well, you get Kip Thorne. He's this incredible figure who lives right at the intersection of, mind-bending theoretical science and huge, blockbuster Hollywood storytelling. Today, we're going to unpack his amazing journey.
And right there, that quote tells you everything you need to know about the scale we're playing with today. We're talking about a 100-year journey, from a wild idea on a piece of paper to a discovery that literally changed history. Thorne's whole career is built on this idea of standing on the shoulders of giants and just pushing the absolute limits of what we think we know.
All right, let's start with probably his most famous project, the movie Interstellar. Now, this was so much more than just a sci-fi flick. You can almost think of it as a Trojan horse, sneaking real gravitational physics into the minds of millions of people, because the science was baked in from day one. But was it all legit?
This was actually the first big challenge that came from astrophysicist Neil deGrasse Tyson. I mean, it's a fair question, right? With all our modern tech, gene editing and everything, wouldn't it just be way, way easier to fix the crops than to, build spaceships, fly through a wormhole, and colonize a whole new planet?
And what's so cool is Thorne's answer to this. He didn't just make something up for the plot, no. He actually went and talked to top biologists at Caltech. And they told him, look, a vicious blight that attacks many different kinds of crops at once, that's basically unheard of. But, and this is the key part, they couldn't scientifically say it was impossible. So the movie's entire premise lives in that tiny, terrifying sliver of scientific possibility. Okay, so the next big issue people had was that massive planet-sized wave. Tsunamis here on Earth just don't work like that. They're these broad walls of water, and they suck the water away from the shore before they hit. So where in the world did this single, impossibly huge, peaked wave come from?
Turns out, Thorne had an answer for that too, and it's based on a real, although pretty rare phenomenon called a solitary wave. It's this perfectly stable wave that can travel for huge distances without losing its shape. Now, obviously the movie's version was cranked up to 11 for drama, but the physics behind it, absolutely real.
But this is the big one, the time dilation. To get that crazy ratio, 1 hour on the planet equals 7 years for everybody else, that planet would have to be orbiting insanely close to the black hole. So close that all the physics we know says it should be unstable, that it should just spiral right in and be destroyed.
And this is where the story gets really good. The director, Christopher Nolan, absolutely insisted on that 1 hour to 7 years thing. Thorne's immediate gut reaction was, nope, impossible. But Nolan just said, go do the math. So Thorne did, and he was blown away to discover that yes, it is possible if the black hole is spinning at almost its maximum possible speed. A brand new scientific insight, all because a movie director wouldn't take no for an answer.
So you can see how this dedication to getting the science right pushed Thorne from just making movies into exploring the really out there theoretical frontiers of physics. We're talking wormholes and even time travel. And believe it or not, it all started with a phone call. The legendary Carl Sagan was writing his novel, Contact, and he had his main character traveling through a black hole. Thorne had to tell him, Carl, that's a one-way trip to getting spaghettified. What you really need is a wormhole. The only catch? At the time, they were thought to collapse in an instant. So Thorne, being Thorne, got to work. He calculated that you could theoretically prop a wormhole open, but you'd need something called exotic matter. Basically stuff with negative energy that repels gravity. Instead of attracting it, it pushes instead of pulls. And before you say that's just sci-fi, there's a real measurable quantum phenomenon called the Casimir effect that's kinda similar. It's not just fantasy. Okay, so if you have a stable wormhole, does that mean you can build a time machine? Well, the physics seems to say no. It turns out the moment you could travel back in time, even just a tiny fraction of a second, these random quantum fluctuations would start a feedback loop. Think of it like putting a microphone next to a speaker. You get that horrible screech. The energy would build and build infinitely until the whole thing just explodes. Or, as Thorne's good friend and colleague Stephen Hawking so brilliantly put it, the laws of physics have this built-in protection system, a kind of cosmic censorship that luckily keeps the universe safe for historians. Just a perfect, witty way to close the book on that debate. So now we're going to shift gears from the purely theoretical to something very, very real. We're talking about Thorne's crowning achievement, not in a movie, but in reality.
the 50-year-long quest to finally hear the universe's most silent song, to detect gravitational waves.
Now, to pull this off, the LIGO experiment had to measure a distortion in space-time as a gravitational wave passed through it. How small of a distortion, you ask? A change in distance just 1/10,000th the width of a single proton. I mean, let that sink in. That is an almost unbelievably, incomprehensibly small measurement.
In fact, it was so mind-bogglingly difficult that when Kip Thorne first heard about the idea, way back in the early 70s, his first thought was, and I quote, "That's crazy. It's impossible." So yeah, even the guy who would one day win the Nobel Prize for it thought it couldn't be done.
But, science just keeps pushing. And this timeline shows you the incredible persistence it took. It all started with pioneers like Joe Weber back in the 60s. Then in '72, Rai Weiss came up with a laser-based design that would change everything. It took 3 more years just for Thorne to convince himself the crazy idea was actually possible. And from there, it was a nearly half-century marathon of work that all led to that first faint signal in 2015, and then finally, the Nobel Prize.
So what does a career like Kip Thorne's really teach us about how we make discoveries? Well, his work, both on the movie set and in the lab, it shows us some really profound truths about how modern science actually happens.
The big takeaway here is that modern science isn't about some lone genius having a eureka moment. As Thorne himself says, the LIGO Nobel Prize really belongs to 1,000 people. These massive discoveries are built across generations. They take decades of pure persistence. And they're not just about brilliant ideas. They're about incredible engineering, fighting for funding, and navigating all kinds of hurdles. Thorne brings up this famous quote from Isaac Newton all the time, and it just perfectly captures the spirit of his entire career. Every single breakthrough we make is only possible because of the foundation that was laid by everyone who came before. That, right there, is the essence of how science moves forward.
Which really just leaves us with one last question to chew on. Kip Thorne's story shows us what it really takes to do the impossible. Decades of work, thousands of people, and just this unshakable belief. So, what's next? What's the crazy idea that scientists are arguing about right now that's going to be the Nobel-winning discovery of, say, 2074?